for you. In this video, we consider the mutual inductance of plain circular coils which are kept concentric and coplanar. So let us consider a circular coil of radius R1 with the N1 turns and another coil, another circular coil of radius R2 with the N2 number of turns. They are kept concentric and coplanar as shown in the figure. And let us consider the current is flowing through the outer coil. Suppose the current is flowing through the outer coil. There will be a magnetic field produced through the axis of the outer coil, I mean inside the outer coil. Within that magnetic field, the circular coil, the inner circular coil is coming. So, the magnetic field is linked with the inner circular coil area and there is a flux linkage with the inner circular coil. Now, that flux linkage flux linked with the inner coil will be directly proportional to the current I flowing through the outer coil. And therefore, flux phi is equal to M into I. Flux phi equal to M into I, where M is the mutual inductance for the pair of coils. The same flux we consider in terms of the magnetic field and area. Magnetic field and area. So when I take that flux phi is equal to flux linked with the inner coil will be equal to magnetic field produced by the outer coil into total number of turns N1 inner turns into pi R1 square. So this is the total area inside the magnetic field. And therefore flux phi will be equal to magnetic field inside the outer coil will be mu 0 N2 into I divided by 2 R2 derived formula into N1 into pi R1 square. So I can rewrite this as phi equal to mu 0 N1 into N2 into pi R1 square into I divided by 2 R2. So this is equation number 2, I could say. So when you compare equation 1 and equation 2, we can see that the mutual inductance M will be equal to mu 0 N1 into N2 into pi R1 square divided by 2 R2. So, mutual inductance of the pair of coils depends on whatever factors you can see from this one. Okay? Now, there is a special case that suppose the current is flowing through the inner coil, then what will be the case? Now, if you assume that the current I is flowing through the inner coil, let us see, then there will be a magnetic field produced inside this coil, and in that magnetic field, a part of the area of the outer coil is now coming into that field. So, a part of the area of the outer coil is now mingling with the magnetic field produced by the inner coil. Therefore, there is a flux linkage with the outer coil. So, again we start with flux phi linked with the outer coil will be directly proportional to the current flowing through the inner coil. So that phi equal to m into I. Equation 1, there is no change. But when we consider the flux in terms of magnetic fields, here, what happens is, let us see. Now flux phi equal to magnetic field produced inside the inner coil into the total area of the outer coil inside the magnetic field. So magnetic field is present only in this particular area. Therefore, this much area of the outer coil is coming into the magnetic field. That means N2 into pi R1 square it will be. Okay? Now, let us see what happens. Flux phi is equal to, what is V? Mu 0 N1 into I divided by 2R1 into N2 into pi R1 square it is. Therefore, flux phi is equal to mu 0 N1 into N2 into pi R1 into I divided by 2 it becomes. Because R1 and 1 from this cancels and you will left with this. And this is the equation number 2, and when you compare this and this, you will be getting the mutual inductance M. When the current is flowing through the inner coil, it will be mu 0 N1 N2 into pi R1 divided by 2. So if I take this as M1, current flowing through the inner coil, and this as M2 as the current flowing through the outer coil, then M1 and M2, you find some difference there between the two. So inner coil and outer coil. But this differences with what? The radii R1 and R2. Here only R1 is coming. Now if I apply an approximation that if R1 is almost equal to R2, that means the two coils are closely wound. One upon the other, closely wound, then the radii are almost the same. If the radii are almost same, then R1 from this goes. For this particular case, you will be getting M equal to M2. So for a closely wound plain loops, the mutual inductance of the pair of loops will be equal. Means mu 0 N1 N2 pi R1 by 2, and there also you will be getting the same. So these are all the special cases. Remember, difference is there for outer coil carrying current. This is coming like this. Inner coil is like this. But only when this R1 is equal to R2, closely wound, then you will be getting the equation M1 is equal to M2. That means for a given pair of coil, if it is closely wound, then the mutual inductance is found to be the same. irrespective of the current, whether it is flowing through the inner coil or through the outer coil. Okay.